Hello all. So, welcome to this new lecture in the course on time series modeling and forecasting using R. So, now if you vaguely remember in the last section, we kind of played around with a practical example in R, right. And now it is a new week, so we will start with a slightly different idea, which is how do you capture non-stationarity. Because remember one thing, that almost all the practical examples that you see around, so be it sales data or stock price data or let us say temperature data etc., would be non-stationary, right, because there will be some trend component or there might be some seasonality or some cyclicality, or in general there might be some patterns, right. So, one can't expect that the practical data set will be stationary to start with, right. So, analyzing any non-stationary data becomes all the more important. Okay. Alright, so initially you have, so exactly what we spoke about in just a short while back is kind of summarized here. So, by the way, the first step in the analysis of any time series data is to plot the data, right. So, for example, if you kind of plot the data like that, so if the data shows some trend, then one can actually identify that the data set or the time series is not stationary. Okay. So, if the time series behaves as if they have no fixed mean level, for example, even here the mean is not fixed, the mean is keep on changing. For example, initially the mean is that level, then the mean level changes to that level, right, and then eventually the mean could be somewhere here. So, as long as the mean is not fixed, then one can say that the data set is not stationary. Okay. But then many a times, however, although there is no fixed mean, one can actually see that parts of the time series or local, so what we call as local parts of the series display a certain kind of homogeneity, in a sense that local behavior is observed or on shorter intervals. So, what do you mean by that? So, for example, here let us say if I draw a fresh plot, right. So, let us say overall there might not be a trend as such, but let us say so initially you have a trend which is upward, then probably downward, right, and then probably upward again for a while, and then probably again downward, and then continues like that, right. So, here you see that even though you do not have an overall upward trend or a downward trend, but in local behavior or local intervals, for example, here and then probably here and then probably here, you see that in smaller local intervals one can observe some trends. Okay. And then this is exactly what we mean by again a non-stationary kind of a series, because the mean is changing throughout, right. So, initially the mean could be somewhere here, let us say, then the mean changes to that level, right, then again it comes down to that level, then probably it again increases to that level. So, overall again, even if you do not have an overall trend or overall seasonality, but the time series may possess some patterns or some replications in a shorter span or a shorter interval. Alright. So, this is a small definition of when can you say that a series is stationary or not stationary. Okay. So, now analyzing any non-stationary series, one has to do a lot of refinements, right. So, probably from all the previous lectures, if you recall, that one idea to correct non-stationarity is transformation, right. So, let me just write it down, that one can actually correct non-stationarity by transformation also, right. So, one can correct non-stationarity by transformation, but then now here we will see two operators, right. And so, the idea of these two operators is that if you operate these operators on any time series process yt, it again helps to kind of correct some of the non-stationary ideas, right. And I think both the operators are kind of easily defined. So, the first one is called as Backshift operator. So, what do you mean by Backshift operator? So, the Backshift operator notation wise is capital B, and then this Backshift operator is a really important operator when it comes to defining the time series lags. Now, the definition of this Backshift operator is kind of easy. So, if you apply this B on any time series process yt for that matter, right. So, the resultant should be yt minus 1, and hence the name Backshift. So, what you are doing is you are kind of shifting the time span by one time span in the history, right. So, if you apply this Backshift operator B on let us say yt, it should produce yt minus 1. Now, again you may wonder that what would happen if you apply this Backshift operator number of times, right. So, let us say twice. So, one can do that, right. So, b square of yt. So, what do you mean by b square of yt? So, b square of yt means nothing but if you apply this Backshift operator twice, right. So, essentially this b square of yt is nothing but if you are applying this Backshift operator twice on yt. So, something like b on b of yt, right, something like that. So, b of yt is yt minus 1, and then b applied on yt minus 1 is yt minus 2. Okay. So, hence if you apply this b on yt minus 1, then again you should backshift the time span by 1 unit, and then the answer should be something like yt minus 2. So, the first operator is really easy. So, the name is backshift operator, and if you apply this b on any time series or current time series value yt, the resultant or the answer should be yt minus 1. And then now I can keep on extending this the same idea, right. So, one can actually apply this backshift operator number of times. So, let us say d times, right. So, b to the power d applied on yt is nothing but y of t minus d, right. So, you kind of reduce the time span by those many units. Okay. So, this is our first operator, and then the second operator is slightly important, which is called a differencing operator, right. So, differencing operator, and then the idea is that by suitable differencing of any non-stationary process, we are able to convert that process to a stationary process. Okay. And by the way, this technique was due to these two people, which are Box and Jenkins. So, by the way, one small point to note here is that Box and Jenkins kind of gave us a lot of different ideas, for example, differencing operator, and then Box and Jenkins have their own methodology by which one can actually analyze a practical time series data set, right. So, how do you convert non-stationary to stationarity, then how do you model any practical time series processes, and so on and so forth. Okay. Now, what exactly do you mean by differencing operator? So, firstly, notation wise. So, by the way, you have an inverted triangle kind of a notation. If you see this, you have an inverted triangle kind of a notation, and then in Greek letters it is called as nabla. So, it is called as a nabla operator. So, N-A-B-L-E. Okay. So, let me rewrite this. So, it is called as nabla in Greek. Alright. And then what happens is, if you apply this nabla operator on any time series process yt. So, in general, nabla to the power d applied on yt is nothing but the dth difference of yt, okay, for all t. So, for example, the first difference would be what? So, first difference would be if you apply this nabla once. So, nabla applied on yt. Okay. So, nabla applied on yt is nothing but yt minus 1. Okay. And then here, as the name suggests, there should be some differencing going on, right. So, this is essentially the differencing that the differencing operator gives you. So, what you are doing is you are taking the current value, which is yt, and you are subtracting one previous value from that. So, yt minus yt minus 1. Okay. So, we covered two operators. So, backshift operator and the nabla operator. Okay. And again, as we saw earlier, so one can keep on applying this nabla operator number of times. So, let us say nabla square of yt, right. So, nabla square of yt would be applying nabla twice. So, nabla applied on nabla yt. Okay. So, by the way, this thing is nabla yt. If you apply nabla on top of that, then so wherever you have t, right, wherever you have t, you basically replace that by t minus 1. Okay. So, for example, here the resulting idea would be something like yt minus 2 yt minus 1 plus yt minus 2, because if you apply this nabla operator on yt minus 1, you would be getting something like this. So, yt minus 1 and then minus, as per the definition, you kind of reduce to t minus 1 now. So, yt minus 1 minus yt minus 2, and then one can combine and then get this result. Okay. So, here nabla operated on yt is hence called as a differenced process. So, initially you start with yt and then you apply this nabla operator on yt to get the differenced process. Now, one very evident question that might come in your head is that what is the relationship between nabla and b? So, is there any relationship at all between the backshift operator b and the differencing operator nabla? And the answer is easy. So, maybe you can pause the video for a second and then try to prove it at your end. But then, so we saw that b is nothing but what? So, b applied on yt, or rather I should write it down this way. So, b applied on yt is nothing but yt minus 1, right. Okay. And yt minus 1 also appears in the nabla definition, which is exactly here, right. So, essentially nabla applied on yt is nothing but yt minus b of yt, isn't it, right. So, yt minus b of yt, because b of yt is nothing but yt minus 1, and then from here I can combine 1 minus b in a bracket operated on yt. Okay. So, this is the relation. So, nabla is kind of similar to 1 minus b. Alright. So, nabla is similar to 1 minus b. Okay. And then this is exactly what you saw here. So, nabla operated on yt is nothing but 1 minus b collectively operated on yt. Right. So, hopefully, if you understand the ideas behind these two operators, so let us say backshift operator and the differencing operator. So, differencing operator is a really powerful tool to kind of convert any non-stationary trend that you have essentially, and then convert that to somewhat mild trend, or the idea behind applying a differencing operator is to reduce the amount of trend or reduce the amount of non-stationarity which is present in the model. So, now we will take up a couple of examples just to understand that how would you make a non-stationary process stationary, right. For example, the first example you see is the linear trend, and then probably all of you must have seen this in our last lectures, right, when we presented some very basic time series models, right. And there we actually saw that you have two ways of kind of concluding that this process is not stationary. So, firstly you have a trend component obviously, and if you find out the mean, so mean itself would depend on t, and then if the mean is depending on t, the process has to be non-stationary, alright. Anyways, but then again if you recall, this is the structure of the linear trend. So, yt equals bt plus st. Now, here what exactly is st? So, st is assumed to be some stationary process, okay. So, st in itself is completely stationary, but then obviously yt is not stationary because it depends on t through this term bt, okay. So, couple of questions. So, is yt stationary? Obviously answer is no, yt is not stationary, and then how would you make it stationary, right. So, how would you make it stationary? Now, if you think about this problem for a second, so applying any transformation won't work here, right. So, let us say if you apply a square root transformation, or if you apply some log transformation, it won't work because the same transformation would appear on the right hand side, and that necessarily won't ignore the idea of t there, right. So, what could be done, right. So, here the nabla operator comes to rescue. So, what one can do is one can apply nabla on yt, right. So, if you apply nabla on yt, what would you have? So, this would be bt plus st minus b and then t minus 1 plus s t minus 1, alright. Now, again blindly apply the formula of nabla. So, nabla applied on yt is what? So, yt minus yt minus 1, okay. So, you take yt as it is and then subtract one prior time point of yt. And here one can clearly see that I can actually cancel out a few things. So, I can cancel out bt minus bt from here, right. So, what is remaining is nothing but st and then plus b and then minus st minus 1, and this clearly is stationary because b is constant and st minus 1 is a function of stationary process which has to be stationary, okay. So, the answer is if you apply a nabla operator once on yt, you are able to kind of reduce the non-stationarity and then make it stationary in a sense, okay. And this is exactly what is seen here also. So, let us say if you start with wt, so we are defining wt to be nabla yt, right. So, wt would be yt minus 1, and eventually we will end up getting something like that, which is b plus st minus 1, which is stationary, okay. Now, another example, let us say quadratic trend. So, what would happen if the trend is kind of stronger? So, initially we started with linear trend, and then now the next kind of a trend could be quadratic. So, this is the function. So, yt equals bt square plus st, right. Now, again as before st is a stationary process. So, again the same couple of questions could be asked, that is yt stationary, and then if not, how would you make it stationary? Now, again the clear answer is yt is not stationary, of course, because yt depends through this term on t square, which is a function of time, okay. So, how would you make it stationary? So, we will see. So, if you apply nabla once, would that make it stationary? Probably not, because now the trend is much more stronger, right. So, if you apply this nabla on yt once, it won't work out, right, because nabla of yt would be what? So, bt square plus st minus b of t minus 1 square, and then in a bracket let us say, and then plus st minus 1. Okay. This is nabla operated once. So, if you apply nabla on yt once, one can see that I am not able to kind of cancel out the t terms, okay. I am not able to kind of cancel out the t term. So, bt square plus st minus b of t minus 1 whole square plus st minus 1, all right. So, what could be done here? So, I can essentially apply nabla operator twice, right. So, how about this? So, nabla square applied on yt, okay. So, nabla square applied on yt, possibly you would reduce my yt to a stationary process now, okay, and then we will see how. So, in the next slide it gives an explanation. So, let us say you are defining Wt to be nabla square of yt, then Wt would be something like that, okay. So, yt minus 2 yt minus 1 plus yt minus 2. So, this is the definition of nabla square yt, right. And then if you replace yt here, then eventually you will see that nabla square yt happens to be that guy, which is 2b plus a function of a stationary process which has to be stationary, because b is a constant, okay. So, the underlying conclusion is that depending on how strong your trend is, so whether you have a linear trend or if you have a quadratic trend or if you have a cubic trend, right. So, depending on of what power the trend is, one has to difference the process those many times. For example, if you want to reduce a linear trend, then one should apply nabla once. If you want to apply or if you want to reduce a quadratic trend, then one should apply nabla twice. If you want to reduce a cubic trend, then one should apply nabla thrice, and so on, okay. So, in general, if the trend is a polynomial of order k, right. So, let us say if you have a really curved kind of a trend, so something like almost exponential, so something like that, right. So, obviously nabla being applied once or twice or let us say thrice will not do the job, right. So, let us say if k is bigger than 3, so if k is let us say 6 or 7, right. But what could be done is we can actually difference the process those many times for stationarity, okay. So, hence we saw that the differencing operator is really powerful in kind of reducing any amount of trend that one might have. So, let us say linear trend or quadratic trend or cubic trend or for that matter any higher power also, okay. Now, again we will see a small example which is a random walk, and then I am pretty sure that you must be comfortable with the random walk now, right. So, now again if you recall, this is the structure of the random walk. So, yt equals yt minus 1 plus et. Now, long back in one of my earlier lectures we kind of postulated that why random walk is not stationary, and then again there we kind of gave a proof also, but then just by looking at probably some of the simulations if you remember of a random walk. So, how does a random walk look like? So, random walk is purely non-stationary. So, it would look something like that maybe, where you see an overall upward trend or a downward trend also, right. But then can you kind of prove that a random walk is not stationary by using a slightly different idea? Can you do that? So, let us say yt equals yt minus 1 plus et, and then the question is that why is it non-stationary, right. The question is why is it non-stationary. So, there is a small hint for you. So, think about restructuring this model in terms of a particular AR1 kind of a model structure. So, if you remember AR1, so AR1 looks like this by the way. So, yt equals let us say some c plus phi 1 of yt minus 1 plus et. So, this is nothing but my AR1, isn't it? This is a pure AR1 process. So, can you somehow connect these two models? And one can actually do that, because let us say if you assume c to be 0, right. So, firstly there is no c here. So, c is 0, and what is the value of my phi 1? So, phi 1 happens to be 1 here, right, because phi 1 is nothing but the coefficient attached to yt minus 1, which is, and then since you do not have any coefficients here, the value of phi 1 has to be 1 basically, right. So, by kind of restructuring this AR1 process, I can actually obtain a random walk model. And then if you remember when we discussed the topic on AR1 and its properties as to when would an AR1 be stationary and so on. If you vaguely remember, any AR1 model would be stationary whenever this coefficient phi 1 is strictly between minus 1 and 1, right. So, we had a small argument there that whenever the coefficient phi 1 is strictly between minus 1 and 1, the process would be completely stationary, right. But in this situation we do not have that, because phi 1 is exactly equal to 1. Right. So, phi 1 is not strictly less than 1, and hence this random walk happens to be not stationary. Makes sense? So, this is a slightly different argument. So, if you are kind of sitting in a time series course, so one should be comfortable enough to kind of restructure the model as and when possible to a slightly different kind of a model and then argue accordingly, right. So, if you start with a random walk, one can actually restructure this into a possible AR1 kind of a model structure. And then since the coefficient value is exactly equal to 1, the model has to be non-stationary, because for any AR1 model to be stationary, the coefficient is needed to be entirely between -1 and 1, which is not happening in this case. Okay. Now, one evident question is, what about nabla yt though? So we will see what happens. So, nabla yt is what? So, nabla yt is nothing but yt minus 1. So, again if you come back to this random walk structure, so here we will see that yt minus 1 if you do is nothing but et, and et is nothing but entirely stationary, right, because et is a random error or a white noise kind of a term. Okay. So, nabla yt happens to be stationary, but yt itself, hence is a random walk, is not stationary. Okay. So, essentially what is happening is, let us say this is my yt, right. So, this is one simulation of a random walk, but if you difference this once, right, if you difference this once, for example, if you take something like nabla yt, then the picture would be different. So, nabla yt is hopefully stationary, something like that. Alright. So, just a small example of a particular case where you are trying to analyze a random walk. Okay. Now, we will kind of shift attention to seasonal models. So, so down the line probably we will spend some time on kind of modeling seasonality using a particular ARIMA structure also, which is SARIMA by the way. So far we have not introduced ARIMA also, so we will do it subsequently. But then a quick idea as to how would you apply the differencing operator if seasonality is present. Now, a few very quick examples of seasonality just to recall. So, let us say airline passengers or sales data, or let us say accidents data. So, all these examples there has to be some seasonality present, or let us say rainfall data, temperature data, humidity data, etc. Okay. And then classical decomposition model is given by that model. So, let us say your time series value yt could be broken down into 3 parts. So, mt, small st and big st. So, what is mt? So, mt is a pure trend component, small st is nothing but a pure seasonal component with a particular period. So, period d. So, we will talk about what you mean by this period very soon. And then lastly, as seen before also, this capital St is a purely stationary process, right. So, my yt is broken down into a trend component, seasonality component and a purely stationary component. Okay. Now, differencing at lag d. So, slightly different idea. So, differencing at lag d and how exactly things are changing here. So, let us say what do you mean by when you apply the lag d difference. So, we call this difference as lag d difference. Notation is slightly different. So, let us say Wt is nabla subscript d rather than power. So, nabla subscript d operated on yt. Okay. So, the lag d difference is nothing but you take the difference between the current value and the dth lagged value. So, yt minus d. So, again if you remember a quick revision, so nabla yt was what? So, nabla yt was nothing but yt minus 1, right. So, essentially my nabla yt is nothing but lag 1 difference, right. So, this is called as lag 1 difference, alright. And then if you want to take, let us say nabla 2 as a subscript of yt. So, what is this? So, this is nothing but my lag 2 difference, alright. And then lag 2 difference would be what? So, you are taking a difference between yt and yt minus 2 directly, okay, and so on. So, lag 3 difference, lag 4 difference. So, in general what do you mean by lag d difference? So, lag d difference is you are taking a difference between yt and its dth lag. So, yt minus yt minus d. Okay. So, let us see that what would happen if you take a lag d difference of the classical decomposition model that we saw earlier. So, what would you have is you will have something like this. So, mt minus d plus the difference between the stationary version. Okay. So, a particular lag d difference kind of completely ignores or completely reduces the seasonality aspect. So, as a small comment, so a lag d difference removes seasonality of period d. So, here since you do not see any small st minus d, because small st minus d would be kind of 0. Okay. So, if one wants to correct seasonality, then one has to apply a lag d difference. If one has to correct trend or one has to reduce trend, then one can actually apply either nabla or nabla square or nabla cube or in general nabla to the power d. So, hopefully the idea is clear. So, on one hand you have nabla to the power d and on the other hand you have nabla subscript d, which is called as lag d difference. Alright. So, here we have clearly seen that if you want to reduce seasonality, then one should actually take a lag d difference on the time series process yt. Okay. Now, what exactly do you mean by this period d? So, any seasonal time series comes with some particular repetitions, right. So, let us say temperature data. So, now if you see the temperature data, if you try to draw the plot of temperatures, so it would be seasonal obviously, right. So, let us say all the peaks are nothing but summer months. So, let us say June of a particular year, then the June of next year, then the June of next year, and so on. So, all these could be June or July months, and all the troughs could be, let us say, December or January. So, I will write down D for December, and then the plot is, so on the x axis you have all the years, and on the y axis you have the temperatures, right. So, let us say this is in 2000, then in 2001, then 2002, etc. Okay. So, here if you see a repeating pattern, because it has to be repeating because the time series is seasonal, but how exactly it is repeating. So, let us say so you have a repetition which is kind of occurring after every 12 months, isn't it? Because here you are seeing peaks which are repeating themselves after every 12 months. So, June of a particular year and the June of the next year, so 12 months have gone, you see a similar kind of a temperature, and similarly all the troughs, right. So, for a temperature data, one can say that you have a seasonality of period 12, because you see repetitions after every 12 months. Okay. So, in general, what do you mean by period d now? So, period d means if the seasonality is being repeated after every d periods, all right, rather than 12. Okay. Make sense? So, I will give you one more question. So, what do you mean by, let us say, seasonality of period 4? So, seasonality of period 4 could mean that something is being repeated every quarter. So, let us say in January, then the next thing is in April, then the next thing is in July, and then the last thing is in October. Okay. So, if something is repeated after every quarter, then the period is 4, or if something is being repeated after every 12 months, then the period could be 12. Okay. So, depending on how the repetitions are occurring in a seasonal time series, one can actually define the period of seasonality, right. And the last statement here is that depending on what period of seasonality you have, one has to apply lag d difference to kind of remove that seasonality aspect. Okay. So, now the last thing we will discuss is the definition of ARIMA PDQ process. So, how do you define the ARIMA process? So, by the way, full form of ARIMA is autoregressive integrated moving average, alright. So, autoregressive integrated moving average. So, this ARIMA process has two components, so an AR component and a ME component, but then there has to be some trend in the data also. So, ARIMA is a classic example of non-stationary series to start with, and any ARIMA process comes with 3 orders or a triplet of orders. So, P, D, Q. Okay. And then definition is kind of easy if you read this multiple times. So, what exactly is a ARIMA process? So, any non-stationary time series process yt follows a particular ARIMA P, D, Q model if the dth difference. So, by the way, this is not lag d difference, this is a dth difference, right. So, nabla to the power d. If the dth difference, which is nothing but produced by differencing yt d times, is a stationary ARIMA PQ process. So, what do you mean by that? So, let us say, so initially let us say you have a time series yt, and yt is assumed to be modeled using an ARIMA process, alright. And then since yt is not stationary, it has to have a strong trend component. So, let us say what we do is we difference this d times, alright. So, we apply nabla d times, and then the resulting series, which is let us say wt in this case. So, wt happens to be a stationary ARIMA process with orders p, q, and then you have an assumption here that this process should be stationary. So, essentially what you are doing is, if you are starting with some ARIMA model and differencing that ARIMA process d times, so as to get a stationary ARIMA process of orders pq, then this initial yt that I have, so initial yt has to be modeled using an ARIMA P, D, Q process. So, here again just to summarize, the idea is kind of easy, that the so P order stands for the autoregressive order, the Q order stands for the moving average order, and then D stands for how many times you want to difference. So, I will take a simple example. So, let us say you start with yt, and then yt is assumed to be non-stationary with some trend component. So, you have some strong trend, okay. And then let us say if you apply nabla 2 times, alright. So, if you apply nabla 2 times, and then the resulting series WT happens to be a stationary ARIMA process with orders 2, 1, let us say. Right. Now, just pause the video for a second and then tell me that what could be the model for the initial time series YT. So, what is the answer? So, again just to summarize, so since you started with YT and then you applied the differencing operator twice to obtain a stationary ARIMA process with orders 2, 1. So, my initial YT process should be ARIMA with orders 2, 2, 1. So, why 2, 2, 1? Because AR order is 2, MA order is 1 from this ARIMA 2, 1, and then since you have differenced this twice, the middle order is also 2. Okay. So, probably in the next session we will kind of revise this ARIMA process if you want one more time, and then probably subsequently we will try to extend this to a particular seasonal ARIMA process, it is called as SARIMA. Okay. And then we will kind of talk about its properties and probably some examples, so as to understand this ARIMA process and the subsequent forecasting in a easy way. Thank you.